Good evening. Good evening all. We have a two-hander session this evening. I'm Jeremy Bennett. I'll be speaking jointly with my colleague Kerstin Eder, and we'll be chopping and changing halfway through as we talk to you about the subject of energy. So, why are we concerned about energy? Well, here's a phone from a bit over a decade ago. It's an Ericsson T65, released 2001, lithium-ion battery, and you could have it on for a couple of weeks and you'd still have some battery life left, and you could talk to people for 11 hours without any problem. And it actually had very good prediction. It actually knew how to predict how much energy you got left, tell you how much longer you keep talking. A couple of years ago, we got the Sony Xperia. It's got a bigger battery, but notice how batteries haven't got much bigger in the same size phone. It's only a little bit bigger. And it hasn't got a longer standby time, and its talk time is only about a third. So as technology's advanced, we put more and more stuff in the phone, we want to do more and more computing with it, and the consequence of batteries not being bigger is the phone goes flat quicker. And if I put on there something like a Samsung Galaxy S4, the battery there is huge. It's why the phone's so big. It's 2,600 milliamp hours, but the talk time, the standby time aren't much longer even so. This is an issue that, while it may be immediately apparent to your mobile phone, affects everything. At the power station level, Google burns about 1 gigawatt a year powering its data centers, and that costs Google about $1 gigadollar. So there's a strong financial incentive, leave alone the environmental incentive, to save energy in data centers. Now, you may think when you transact things over the internet that Google is all to blame, but not really, because some recent research shows that where a lot of that power goes is actually in the router in everyone's homes. If you're streaming a movie, about 97% of the energy cost is actually in your home, and most of that is in the router. The mobile phone we've already discussed, the batteries get bigger and bigger, but the phone lasts less and less. A couple of other areas. It may seem strange, but an electricity meter actually has a battery in it these days, and the most expensive thing about your electricity meter is the guy who comes out every 10 years to change the battery. And if he doesn't change the battery, you don't get metered and you get your electricity for free. If you can make that battery last another year, you take significant costs off the energy company. And lastly, energy scavenging. Now, where Google may concern itself with gigawatts, energy scavenging devices concern themselves with nanowatts. And for them, energy saved is more computation that can be done. Just to clarify some basic mathematics here, when I talk about energy and power, they have precise meanings. Power is how fast you're burning the energy. So you multiply the power by the time and you get the total energy used. And generally, it's the total amount of energy that matters. So we can burn a lot of power for a short time, and that's just as good as burning a little power for a long time. Of course, you can turn that equation the other way around. Now, I don't want to give the impression that people haven't been working hard. Hardware engineers are actually very good at energy efficiency. So here's the circuit of a standard inverter in CMOS. On the left, we see the inverter when it's input high, so the low transistor, the NMOS one, is turned on, and the capacitance of the circuit has to be drained out. So that's energy being used. And when I switch it the other way, I've got to charge all that capacitance up, and that uses energy. So each time I switch, current's flowing, and current flowing is energy used. In addition, as I switch between the two, there's a period when both transistors are on, as one turns off and the other turns on, and then I've got a short circuit, and that's draining current. So the effect of that, that's dynamic. The faster I switch, the more I'm going to lose energy. That's what we call dynamic energy loss. Now, if you remember your school child electronics, power is proportional to voltage squared times the resistance. We're also, in this case, losing that every time we switch, so we're proportional to the frequency. So the power is proportional to V squared R times the frequency. And since frequency in chips is generally proportional to the voltage, the higher frequency you want to run, the higher you have to put the voltage up you run your chip on. So we actually find power is proportional to the cube of the frequency you run your chip at. And if you multiply it by time to get energy, of course, if you run your chip slower, you have to use that power for longer. So actually the energy is proportional to the frequency squared or the voltage squared. But that's only part of the energy loss. We also lose energy through current just leaking through. If you look, there's a cross-section of a modern chip. The actual layer between the gate and the underlying substrate is just 4 atoms thick. Make it 5 atoms thick, it won't be sensitive enough. Make it 3 atoms too thick, and you'll just have quantum tunneling, losing all your electrons through to the substrate. But you're still going to lose some. You're going to lose some through ordinary current just draining through the resistance, and you're going to lose some through quantum tunneling. And indeed, you're going to lose some from side to side of the chip as the source and drain connect, both through traditional resistive flow and also through quantum tunneling. And that's just static loss. It's going to happen whatever you do. So long as you've got power on that chip, whether you switch it or not, you're going to get static energy loss. It's still V squared R, but we don't care about the frequency now. So since frequency and voltage are still related, power is proportional to the square of the frequency. Multiply the time in there. Energy loss due to static loss is proportional to the voltage, and to 1 over the energy is proportional to the frequency. Now what this means is that dropping the frequency of your chip so that you can actually reduce the voltage is a huge winner. And that's why in your mobile phone you get 4 or 8 cores, because it's much better to run 4 or 8 cores at a very low frequency and low voltage than it is to run 1 core at a high frequency. But that's not all you can do. You can switch off when you're not actually doing anything. Now you're used to power saving modes on your laptop and so forth, but actually hardware electronics does it at a far finer grain level, what's called clock gating, not using part of the circuit. Let's turn the gate off, let's not clock it at all, let's not do anything with it. And we can see all those effects if we look at modern chips. And I've got an example here. It's from the Atmel AVR range. If you use an Arduino, you're familiar with these. This is actually a slightly different one. It's an ATX Mega 256. Run it at 3 volts and 2 megahertz, which is the standard configuration, and even in standby it'll draw 290 microamps. It's a small current, but it's still a current. If you don't have to do much computing, you can drop down to 32 kilohertz, and then you can run at 1.8 volts, and then its standby current is just 4 microamps, and that means you can run an awfully large number of years on your battery. So, hardware engineering has done a great deal to try and save our battery, but we still have our mobile phones going flat, and we still have the Googles, the Facebooks of this world doing their best to contribute to global warming. And at this point, I'm going to hand over to Kerstin, who's going to explain how software engineers and the open source community are going to save the world.
That's a challenge to live up to. Thank you very much, Jeremy. I'm Kerstin Eder. I'm a computer scientist, and I'm from Bristol University. And I would like to introduce you to an idea of energy transparency, which I believe is the key to us as computer scientists, or as programmers, gaining better understanding of how much energy is actually consumed by the code we write. And I think we better get on with this because it's really important. We don't want news like this, right? That's the sort of news we want to avoid, because at the moment it seems that the hardware community has done an awful lot, but the software community is very much blissfully unaware of this. Right, so let's sum up. Power management has largely been in the hardware domain, as Jeremy explained. There's dynamic and static power, there's energy consumption, which is a first-class design goal for hardware designers. There's on-chip power management, dynamic voltage and frequency scaling. There's different modes: standby, suspend, sleep, off, on. They're all having different effects on the power consumption of the hardware. But are we actually focusing on the right area? Are we focusing on where the greatest savings can be made? When I started looking at this, I saw a slide from Mentor Graphics, and they explained where it's most efficient, or where you can get the biggest gains in terms of power optimization. And what was said was that that is at the highest level of the design hierarchy. But hang on, as a computer scientist, I know that that is not the top of the system stack, right? That might be for hardware, but as a computer scientist, I know there's layers above that. And so the focus really is on software. And interestingly, when I got into this, there was this interesting article in the Electronics Weekly. The heading is interesting: lack of software support marks the low power scorecard at DUG. What's in the caption is also interesting: Intel waits for better low power software control, right? So really the focus is on us. Let me talk you through this. It says it is becoming clear that the system level is currently the missing link. But if the software keeps cores active for no good reason, the low switching power per bit processed won't deliver a realized saving. Here's an interesting fact. Someone from Intel said that with limited software support, dedicated low-power circuitry could save maybe 20% in a typical multimedia-oriented core. But if we make the software better at controlling the power states, that difference could be 3 to 5 times. So there's a lot to gain if we really look at software. Now the question is whether we can take the actual use cases into consideration and optimize the software to power the logic circuits down. We still have a long way to go, and the last bit is really interesting, because this is the bit that talks to us. We should put a challenge to the software designers to see how much power they can save, right? It's a clear switch from hardware to software. The ball is in our court. Right, so huge advances have been made in terms of power-efficient hardware. There is lots of software controllable energy-saving features available, but the potential savings are wasted effectively by software that does not exploit them, and by poor dynamic management of tasks and resources. So we really need to learn about this stuff to make our software more energy efficient. Now the focus is very much on software, because it is the software that controls what the hardware does. Ultimately, it is the algorithms, the data flow, the compilers, the optimizations that the compilers realize. But the problem is, the traditional software design goals are performance, performance, performance. So we're blissfully unaware of what effect algorithms, data structures, and codings have on the power consumption of the energy use of our code. At best, energy is a secondary design goal for us. But we can't get around the fact that the biggest savings can be achieved by optimizations at the higher levels of abstraction, and that includes algorithms, data, and software. Here's an interesting article. When I got into this, I read this article, and I would like to talk you through this. It is literally the last passage of an article that I read, and it started with, if you want to align your software design decisions with energy efficiency as a design goal, you have to follow the following steps. And that is in quotes, so that really is coming from an article. First step, choose the best algorithm for the problem at hand and make sure it fits well with the computational hardware. Failure to do this leads to costs far exceeding the benefit of more localized power optimization. So there's a little warning here. But how many of us think, when we select an algorithm, how that maps to the hardware? Next step, minimize memory size and expensive memory access through algorithm transformations, efficient mapping of data into memory, and optimal use of memory bandwidths, registers, and cache. Next step, optimize the performance of the application, making maximum use of available parallelism. Next step, take advantage of hardware support for power management. That's the fourth step down. That is when we consider what the hardware makes available to us. And then finally, select instructions, sequence them, and order operations in a way that minimizes switching in the CPU and data path. So that's when you minimize the bit twiddles effectively during the computation. Any guesses how old this article might be? When might it have been written? When do you reckon?
1960s.
Ah, good guess. 97. So 1960s, well, 1997. But since then, not much has changed for the software community, right? And that is really interesting. Here is the starting point of this article. Something that starts with, it is tempting to suppose that only hardware dissipates power, not software. However, that would be analogous to postulating that only automobiles burn gasoline, not people, right? That is worth reading, and it's a really good article. I recommend this to all my first years. Right, so that leads me to something interesting. We can't optimize something that we can't see. So for me, energy transparency means that information and energy usage is available for programs, ideally without having to run them, at all levels of abstraction between machine code and high-level application code. We need to see it before we can optimize it, so we can better understand which algorithm to choose for which battery life, right? At the moment, we have very poor visibility of this, if any. Now, we know that the principle of transparency works. We know this from different parts of life. We can make decisions about what we consume based on transparent information. Right? We make other decisions in life because resource usage is transparent to us. And here's one that I really like. This is the back of an Italian rail card that shows you how much CO2 is caused by different modes of transport for different destinations. Now really what you want is you don't want these point solutions. You want a function. You want a function that tells you, in terms of properties of the input data, and potentially also properties of the target hardware platform, what is the energy consumption of the code that you're proposing? Right, so you can then see in which space you're working. So, from my point of view, energy transparency enables a deeper understanding of how algorithms and code impact on the energy consumption of a computation when it's executed on a particular target platform. Now, this is critically important, and one can enable this in various different ways. One of them is doing it dynamically by actually measuring it. Here is one board, which Jeremy is going to explain a little about later on. Our second-year students have embarked on a design of an API, which is called the Energy Aware Computing Framework. It's available on GitHub since 2 days ago. And that API allows you to put library calls into your code and connect it on the other side to some energy probes which you have available, and then you can get interesting data about your algorithms. So this is what we've done. We've sorted integers between 0 and 255, but encoded using 8, 16, 32, or 64-bit. And these are different sorting algorithms, so don't compare between the rows, just between the columns. And that's becoming interesting. You can get interesting results. So for instance, in insertion sort, the 32-bit version seems to be more optimized, right? You have 102, 103, 104, 105, but it's not 104. Also, for these two sorting algorithms, it seems to take longer to sort 8-bit data than it takes to sort 64-bit data, but more energy is consumed in the process. But because we now have time together with energy and average power, we can make these comparisons, we can see it. So that is what I mean by energy transparency. We should all be able to see this. The other way of achieving energy transparency is by static analysis. Now here's a slide that shows you that ECOF really is available. So you can see, here is the link to ECOF, and that's the web interface, so you can get involved in this API that I've just introduced. Right, so static analysis is another way of doing this, and that's part of the ENTRA project. The ENTRA project is a European-funded project that looks at energy transparency of a whole system. It's in its first year now, and it has a goal which has been part of a Future and Emerging Technologies program, which is focused on minimizing energy consumption of computing to the limit. And one of the target goals is software models and programming methodologies supporting the strive for the energetic limit, and that looks at energy cost awareness or exploiting the trade-off between energy, performance and precision. These are the project partners: Roskilde, University of Bristol, Imdea Software and Exmos as our industrial partner. And in the Entra project we're using static analysis and energy modeling. So we're basically building energy models of processors, and then we're using static analysis to source information from the energy models to tell us upfront how much it might cost to execute a particular function. Right, so let me talk you through a little bit about the energy modeling, because that is the data that enables energy transparency if you want to use static analysis. If you want to know how much it costs to execute a program, then there's a very simple way of doing this. You look at the instructions. So basically, you associate every instruction with a base cost, B, and of course multiply by how often it occurs in your instruction stream. Then you look at the circuit state overhead that is created by switching between two instructions and look at how often that occurs. And then there is other effects like cache misses, pipeline stalls, etc. And you have to add this. And in principle, if you translate your program into a sequence of assembler instructions, then you can figure out with an energy model how much it costs to run this. That's not new, that's quite an old thing, 1996. Now if we look at a more recent processor, you've got multi-cores and multi-threading, so you have to consider also the cost of concurrency. So if you look at a multi-threaded program, you have to look at the cost of the computation being idle, plus also the cost of concurrency in the computation, and that's factored in here. So we've built an energy model for the Exmos X-core processor, and that's about 7%, has a 7% error in there. Now what you can do with this is you can use this to measure energy, to basically source the information from an energy model to find out how much it costs to run a program. Now I always get asked, how do you get to the costs? We actually measure this using boards, and it looks a bit messy on a desk where you basically have a power consumption board and various other boards. Some are target and some are management boards, and Jeremy will talk to you a little bit more about this. But what you end up with is what we call heat maps, and these heat maps give you a good indication as to how much it costs for each instruction to be executed. So what we've got here is a set of instructions, and we've profiled them together running in pairs with all other instructions available, and they are grouped, so any instructions which have like 2 operands are lower energy than any with like 4 or 6 operands. And it's also interesting to see the impact of the data path. So this is for 32-bit data, this is for 8-bit data, and as you would expect, for 8-bit data, the heat map is a lot cooler than if you use 32-bit data. So at that point, I always point out in my first years, when you write int, do you actually think about how many bits this is? And do you actually need that many bits for what you want to do? Because that is the impact of choosing the right data type. And then of course we've done it with a lot more instructions, but the chart is rather large. The point is you can see how much energy is being consumed by each instruction. And based on those models, we can then figure out how much a program consumes based on the statistics of the program, or we can feed this into static resource analysis. And that's the second part, or another part of the Entra project. So, if we do static resource analysis, the algorithms are adaptations of advanced cost analysis and worst-case execution time analysis techniques. They automatically infer upper and lower bounds of energy usage of a given procedure or function. The bounds are expressed as monotonic arithmetic functions for each procedure, parameterized by properties of the input data, such as, for instance, the data size. And then once you've got this, you can do verification. So you can statically determine whether a computation fits a particular budget that you might have in mind. This might all sound a bit theoretical. So to give you a picture, if you think about this as the specified resource usage, you've got the upper and the lower bound. You can plot this. At this time it's in terms of the data size, and you've got your resource, which is energy. And then you statically analyze the code, and these are then the upper and lower bounds that the static analysis has found for your code. And if you've got both available, then you can do verification, and you can see where your program fully meets your specification, where it is not known whether your program meets the specification, and the areas where your program definitely does not meet your specification. And that then can allow us to make the right decisions at the right time with the right information. Right, so what are we doing in the Entra project? We are targeting analysis at different abstraction levels. We've got XC source code, we're using LLVM, and we've got the XC assembly. That's where we have the instruction set architecture energy model. We are now working on an energy model that is based on the LLVM IR. And the first results that we've got actually show us how energy is consumed for a particular function. Okay, the first functions we've analyzed are very simple functions which don't occur that much or not at all in embedded systems. The factorial function in this case, and you can see the hardware measurement is here in blue and the static resource analysis is in green. You can see they pretty much match. So that's quite a good result. And we've done various other functions as well that's been recently published. But the point is, if you've got this available, then you can make the right decisions. At the moment, we are working on a mapping tool which connects our instruction set architecture model to the LLVM IR so that we can easier see what energy is consumed at the ISA level and then translate this into the relevant blocks at the LLVM IR. And that tool will be presented tomorrow at the Energy Efficient Computing Dev Room. Right, so let me summarize. For hardware designers, power has always been and always will be a first-class design goal. Effectively, for a hardware designer, a design is a point in a 2D space. And I've seen an interesting presentation by Mark Horowitz, where he points out that for a hardware designer, you have a 2D plane, and you can find your design in a plane where one axis is energy, the other one is performance. And you can look at this and you can see, and you can also see where the boundary is, so whether you're actually having a good and optimal design. I want this for software engineers. I want effectively more power for software developers. I want to be able to write code where I say in 15 milliseconds do, and then the compiler says no way. But that I can already do. What I want to see is in some millijoules do, and then the compiler says yes or no. Okay? That's what I really want to see. And I would like to see a cool code competition. Some cool programming competition where we say, what is the lowest energy code that we can write to achieve a particular functionality, right? On a target hardware platform, what is the lowest energy code that we can do? To answer the challenge, right? Let's see how much energy they can save. Well, let's tell them what we can save, right? So promoting energy efficiency, the first-class software design goal, is a really urgent research challenge, but it also means we have to engage the community, and that's one reason why we're here. Right, and at this stage,
OpenOffice has crashed.
OpenOffice has crashed. It's gone into save energy mode. So at this stage, I wanted to hand over to Jeremy to let you know more about ongoing projects and compiler work that we do.
Thank you very much. Thank you very much. You may have got the impression from the first part of the talk I'm a hardware engineer. I'm not. I'm a software engineer. The sort of hardware I do involves things like Arduinos and breadboards and my spare time. However, if you work in compilers like I do, you can't actually ignore the hardware. And I want to talk to you about one other aspect of software. Kerstin's already explained how the software engineering is the key to actually getting serious energy improvements. And one place that we can help is potentially by making compilers that are better with regard to energy. Now, this all started a couple of years ago with an argument between two eminent professors in the UK at a meeting I attended as to whether or not the compilers could make a difference. And what became clear from that discussion was that actually neither professor had any data on which to make the assessment. So we set up a small summer project done by a guy who just graduated, 3 months, where we got a lot of little computers, we got some very good current and voltage measurement equipment, and we tried running lots and lots of programs with every different GCC compiler option there is and measured how much energy they took. In fact, we did it 2,000 times for each option just to make sure that we got good, reliable results. And that work actually has now been published. It's an open access publication. We actually paid a small fortune to persuade the Computer Journal to make it open access rather than their usual licensed piracy. As a consequence, you can all read it, and there's the link. And the good news is that compilers can make a big difference to the amount of energy your program consumes. The bad news is it's very hard to work out which options to use for any particular program. So, we have this vision. And what's our vision? Well, today, you typically optimize for either code size or code performance. You've got -OS, and you've got -01, -02, and -03 on mainstream compilers. But what if you could actually have a -OE, optimize for energy? That would be quite something. And as our researchers showed, if you could do that, you can actually make big energy savings. So where did we start from? Well, the project's called the Machine Guided Energy Efficient Compilation, giving the acronym MAGIC. We started off with the sort of research that Kerstin's talked about that's been going on for many years, as we heard, into modelling energy usage. But we realised that any particular compiler optimisation is probably only itself going to have a very small effect, and smaller than anything you could reasonably accurately model. So we'd better measure, and we'd already shown we could do that. So we're going to base it on energy measurement. How much does a computer actually use? But then the next question is, how do we get a compiler to benefit from that? Well, fortunately, there's been a lot of work over the years into what's called feedback-directed optimization, where you run your program, look at what it did, and then use that to select better optimizations. That's quite laborious, particularly if you have to do it lots of times. You can spend weeks just trying to find the right optimizations for the right program. That has actually finished a few years ago. There was a big European project called Milepost. And Milepost said, surely machine learning can help us. We can learn what sorts of programs go with what sorts of optimizations. If we just had enough programs and tried them with all the different optimizations, standard machine learning techniques, we could build up a database of this sort of program goes with this sort of optimization. And that's what they did. It took 3 years, 2 universities, 2 major companies, but they did that. And what they found was that they could get very good results. For something like a Xeon processor, they could do 40% better than -03. Okay? They were optimizing for performance in that case, not energy. It was a performance thing, and they were optimizing for that. So we thought, surely we can use the same technique. We can run lots of programs, all different optimizations, and learn what is the best optimizations for energy efficiency for this sort of program and build up a database. And then anyone coming along with a new program could look in the database, say, that's the optimizations I want, and run with that. Of course, it's all automated. You don't actually look in the database. The compiler goes and does it for you. Of course, that's a great idea. We're a small company. Bristol is a university, and universities never have enough money, but fortunately the UK Technology Strategy Board came riding to the rescue. They're the UK government's innovation arm, and they said, we'll pay. And that's how Magic is funded. It's an 18-month project. It's halfway through. It finishes in November. And our goal is to develop that solution. So what's new? First of all, we're focusing on energy optimization. Secondly, we are using measured energy, not model energy. This is what actual computers use. Thirdly, it's going to be generic. One of the real big problems with Magic, with Milepost, the old Milepost work, it was brilliant and it only worked with GCC 4.4. It was 300,000 lines of patch, and heaven help you if you want to use it anywhere else. Actually, we did help because we migrated it to 4.5 and never again. So Magic is a completely generic framework. It works through the plug-in interface and it will work with GCC, it'll work with LLVM. The early prototypes are already working with both. And the final thing is, there is a catch with getting government money. They're not into blue skies research, this lot. It better be working at the end. So November, we've got to deliver something. And I'm hoping that at the LLVM conferences and GCC conferences later this year, we'll be showing it off. I mentioned energy measurement, and this is where it comes in. You can actually already get very good energy measurement systems. People like Lauterbach will sell them to you, but they cost a small fortune. Certainly not the sort of money that ordinary people, hobbyists, or even small companies like mine can afford to buy. And we thought, actually, it's very easy to measure energy. All you have to do is measure the voltage and measure the current. How do you measure the current? You put a resistor in the power supply and measure the voltage drop over it. The only thing is, we want to do it quite a lot. In fact, we want to do it several million times a second. And we don't want to pay a lot of money for it. And that's where this comes in. This is the 4th generation, I think, of our power measurement board. It's not, this isn't the board, it's the little bit on top to the power measurement board. The thing underneath is an ARM processor on an ST Discovery board. It's a £10 computer board. We just use that to suck all the data off and spit it out on USB. It's the board on top that measures the energy. It's an open hardware design. It's got nothing special in the components. It costs us in small volumes about £30 to make. If this was ever made in mass volume, it will be £2 or £3 each. The nice thing about that is, if you'd like to have a go with one of these, and it can sample 6 million samples a second, it can go down. If you've got a low energy thing that uses 10 milliamps max, we can cope with it. If you've got an energy burning board that burns an amp, we can cope with that as well. The good thing is, we've got 50 of these here. So we're running a workshop in the energy development room tomorrow lunchtime. Come to the dev room tomorrow and you can have a go. You can bring your own kit along and measure it, or we've got a load of Arduinos and ARM boards, you can measure those. So come and learn how to use it tomorrow. And the other thing we need is, if you're going to do this stuff seriously, you need a good benchmark suite. We're fully open source, and that means that we need a good open source benchmark. There are a few around. There's MyBench, there's the worst case execution tests, but there isn't a good set, and all of them assume you're running on Linux and have got printf. And on the whole, these little embedded boards, and they're not all as big as that. There's one I made earlier. That's a little a one-wire thing. They don't have consoles. They're embedded systems. So we've actually put together the Bristol Embecosm Embedded Benchmark Suite, or BEBS, which is a suite of free and open source programs for testing embedded systems. It's got a nice mixture of programs to test floating point, integer, multi-core, and so forth. That'll be developed over the years, and if you've got anything you want to contribute, please let us know. So that's just another project looking at that. I'm going to finish by handing back to Kerstin, who will explain how you can get involved.
So if you want to get involved, there's a few options. You can get involved by coming along tomorrow. We are running an energy efficient computing dev room, fresh and early at 9 o'clock. And this is what you will see. Notice there's a large space over lunchtime where we are actually going to use these boards and measure. And if you're staying to the end, you can take it away. So there'll be we've got 50 of those with us. So if you stay with us to the end, you can take it. But there's other things there as well. There is the ECOF introduced by Hayden Field, who led the second year project. There is the LLVM mapping somewhere here, and the static analysis based on LLVM-IR. So there's all the things that we've introduced you to, basically not explained in detail, and the opportunity for you to bring your own applications and let us measure the energy of the code that you write, so that you get some transparency of your software development and how much energy is consumed. There's also opportunities to get involved after Fosdem. There's the Magic project, which Jeremy introduced, and there's a website, a wiki, a mailing list. They're all open. You can contribute, you can contact us. There's the ECOF, which has got up on GitHub, where you can contribute to. And there's the Entra project, where we are looking at LLVM-IR and as an abstraction level, and you can get involved and contact us on that as well. From Bristol University, if you want to get involved in this sort of context, there's PhD, summer projects, secondments, industrial collaborations, all of those are available. At Bristol, I've started an initiative and a workshop series called Energy Aware Computing, which is an acronym of ECO, and here's the link to see what we've done. There's a set of challenges in terms of energy aware computing, ranging from algorithms down to hardware challenges, and Embecosm is hiring. So if you want to get involved, Jeremy is hiring. Right, so what remains to be said is that we thank you for turning up and listening to us. You can contact us on these emails, and we obviously want to thank all our sponsors, because without them it would not have been possible for us to look at the energy consumption of computing.
Well done, Kerstin.
Thank you. Any questions?
Hi. You mentioned statistical analysis to estimate the energy consumption of the programs you were using. Have you ever tried simulation instead of statistical analysis? Because I know that the mix of instructions that goes through the CPU can actually make quite a bit of a difference in both execution time and power use.
So if I've only heard half of the.
Have you tried simulating for energy?
The question is, have we tried simulating for energy?
Yeah, because I think simulation might be more accurate than statistical analysis.
Actually, if we go back in the slides, you can see the results of the simulation, right? So we've got. I glossed over that a bit, but when I showed you this stuff, there is. So the static analysis is green, the hardware measured is blue, and the statistics-based, trace-based analysis based on the simulation is the yellow line. Yes, we have done that, and we are doing that. There was a question down here?
Yes. Yeah.
Up there.
You have shown a very interesting figures where you are able to provide the amount of power per instruction of the CPU. My question is, how are you sure that you are only measuring this particular instruction? Because if you are running under an OS, you have many things running at the same time. So how can you pin the exact instruction to the exact consumption?
I cannot. So in terms of the instruction-based model, we've got a test suite which has very selected tests, and we're basically running the threads in such a way that they are paired with the right instructions. So we have got a test harness which selects the tests specifically to profile specific instructions.
I think on the wider question, you're concerned about the operating system and what happens if you're running lots of programs at once. The work so far has focused on deeply embedded systems, and deeply embedded systems you're typically running one thing at a time. The other thing, that because we can sample energy with the measurement at such high frequency, for some of the smaller devices we can actually measure the energy consumption of an individual instruction as it executes. So if you come along tomorrow, you'll hear James Pallister talk about some of his work with super optimization for energy, which is based on that.
In addition, the figures that I've shown here are for the X core. There's no operating system running, so you're programming the hardware straight.
Hi. I've got a couple of observations and a couple of questions, if you've got time. First of all, there's a very good book on high-performance web browsing, which covers some of the things that you can do as a web developer to save battery life on mobile, and I would suggest that certain developers around here who are in that space would be advised to read it. The second observation is regarding some of the data center stuff. It would help, I think, a lot if the data center people actually started charging for power as opposed to charging for available power, because this is one of the big reasons why we don't turn our computers off, because it doesn't save us anything to do so. The two questions I've got is, it's very easy for me now to get hold of a profiler which will tell me where my code is running hot in terms of usage. Do you think it's reasonable to expect that kind of sort of 20% of my energy is going in a profiling tool within a sort of the fairly near future? And the second question is, what are you doing to consider things like I/O, in particular network and radio usage?
Okay, I'll answer the first one with that, which is that you can already do it. Companies like Lauterbach and indeed ARM have technology that will allow you to see the profile of your program by energy as well as by speed. And in fact, we ran a workshop in Bristol only a week or so ago where ARM came along and demonstrated profiling by energy rather than compute speed. So you can already do that.
In terms of the I/O, that's a really interesting question, and I've taken some slides out here that mention this, because there's communication and computation, and at the moment I focus solely on computation. The cost of communication can be orders of magnitude higher than the cost of computation. And so in our energy modeling, the next step is to look at the cost of I/O and communication generally. And in the context of the project we are running, this isn't difficult because the I/O is part of the instruction set, so we can model it and characterize it in a similar way to the remaining instructions. We're looking at the moment at other platforms, such as ARM-like platforms, and there the modeling is significantly different. But I fully agree, the cost of communication needs to be considered because it is a large and very costly part of the Michael.
Hey, Kerstin. Yeah, one thing I'm really concerned about when doing energy optimization. Today you have to optimize for a specific implementation of the instruction set. So for the ARM processor by Atmel, that and that model. In the future we will have smaller and smaller structure sizes, so more variability in energy usage. So do you consider it possible to really optimize for a certain fabricated instance of a chip, because that might behave completely different to the next chip coming off the assembly line?
Do you want?
You touch on a very accurate area. When we do the compiler optimization, it is absolutely tied to the particular release. For example, it depends. If you look at some of the deeply embedded, like some of the Atmel chips, the AVR chips, which execute from flash, the optimizations you want depend on the architecture of the flash, how long your bit line is, how long your word line is. And so we anticipate that when you do that optimization database, you will have a database not just for an architecture family, but for a particular issue of a particular chip. And that is one of the challenges, but you've got to do that.
Could everybody who's talking stop, because it's really loud and there's still QA going on, so if you could keep the noise down, that would be perfect. Thank you.
The other answer, Michael, is that we expect with the static analysis that the relativity will still be maintained, but that's to be proven. So if something costs less here, then it should also cost less here or cost more. So sometimes it's the relativity that allows you to choose the right algorithm, and it might not be in absolute values, but the relativity might help. But modulo what Jeremy just explains in terms of flash, etc. Okay.
Thank you all very much.
Thank you very much.
That's the last talk in the tracing and debugging series in this room. However, there is another talk in about 10 minutes on the Fosdem network, which will be by Andrew and Peter from Cisco, and Richard, who will be explaining what's changed in our network this year and all the things you need to know about NAT 6.4 and DNS 6.4.